All right, so we know that type 1 error, chance for making type 1 error, we define it ourselves, and that's our significance level alpha. Now let's discuss what's going on with type 2 error. Okay. So let me remind you that type 2 error is when null hypothesis is wrong, it's false, but you accept it anyway. So in our particular example, it means that lake is contaminated, but the p-value that we get as a result of the test is large enough so we cannot reject null hypothesis. So this is the situation I showed here. So this is what we test, and this is the reality. So this is our null hypothesis, sample size, the alpha. And the question is, how often null hypothesis will not be rejected? Or how likely null hypothesis will not be rejected? That's exactly a chance to make type 2 error. Let me show you how often it will not be rejected, right? So it will not be rejected every time we have a t-value smaller than the critical one, right? This is our critical t-value. You remember that for alpha 0.05, it's 183. I just discussed it in the previous video. So every time we have a t-value here, so it means that our sample average will be here, right? We will not reject the null hypothesis, and that's exactly the situation that we would like to avoid. But every time it's bigger than that, then we reject it. And that's why it's shown green, because in this case, rejection of null hypothesis, it's a good decision, it's a correct decision, right? However, which average values are possible, it depends on the reality. So strictly speaking, average values come from this blue curve. So it's almost not possible to have average value here or here. So average values come from this one, because this is a distribution of the average possible average values for the given sample size in these particular realities that we have, right? So it means that every time we take a new sample of size 10, the average of these 10 glasses of water, for example, the average total ammonia nitrogen will be distributed here. So it will come from this curve. Also, we believe that this is our reality. Okay. Now, how often it will not be rejected? So look, this is exactly the t-score that we have. So it means that if your average values come from this curve, in this case it's t-scores, it's standardized average values, you can see. So it means that every time you are here, you cannot reject null hypothesis. Every time you are here, you will be able to reject null hypothesis. So this is the two situations, and areas of these two areas are probabilities that you will make one or another decision. So the green, you will reject null hypothesis. It's green because in this case it's a correct decision because null hypothesis is wrong. And the red, it's when you cannot reject null hypothesis. In this case, you will make a wrong decision, right? But what the red area depends on, how to reduce red area and increase green area. Well, apparently the situation is more complicated here because there are many factors that influence this. So let me define this again. So this is a red area. It's a chance for type 2 error. And we will use another Greek letter beta for that. So alpha, it's a chance for type 1 error, and beta, it's a chance for type 2 error. And the green area we will call a power of test. So power of test, it's the ability of your test to see an effect to reject null hypothesis if the null hypothesis is wrong. And you can see that it's just 1 minus beta, because how to compute this area is just the total area under the blue curve minus the red area. And that's exactly 1 minus beta. We will use a Greek letter pi for the power of test. Okay. So now let's discuss what these areas depend on, how to reduce red area and how to increase green area. Well, strictly speaking, the power of test, and therefore also the chance for type 2 error, because they are linked, it depends on many things. First of all, it depends on the type of the test and type of distribution you use. For t-test, you have one distribution. For chi-squared test, you have another distribution. And the power depends on the distribution. That's something that we cannot at least change in this particular case. We use t-distribution, but it's important to know about that. Also, it depends on the difference between the test and the reality. So it's a distance between these two peaks, right, between these two curves. The more far reality goes from the test, the more likely, of course, we will be able to see it. The more likely we will be able to reject null hypothesis. It depends on the sample size, because sample size influences the variability. Remember that these are, in this case, it's t-scores. They are related to average of your sample. And remember, the variability of the average of your sample, it's inversely proportional to the sample size, right? So the larger sample size, the smaller this variability will be, and therefore the more clear difference between the test and the reality will be. And it also depends on the significance level, and you will find out why actually people refuse to use small significance level and keep 0.05 in many cases. So let's discuss it step by step. First, I will discuss only these three, but for every distribution, for every type of test, in many statistical software, you can find a procedure, a program, a function that calculates the power for you. So therefore, this is we will not consider different types of tests in this case. So case number one. So this is the situation that we started with, but now I also computed the areas. You can see that this is the power, and this is the chance to make type 2 error. That means that we have, like, if you repeat this many, many times, 60% of the cases, 60% of the situations of the experiments will end up with wrong decision. So we will say, no, lake is not contaminated, also it is. Okay. So the power is 40. The chance that we will see the contamination is 40%. Now, what happens if lake is getting more contaminated? In our case, the real concentration of the TAN, the total ammonia nitrogen, is 22 milligrams per liter. What happens if we have 25? So it increased by 3 milligrams per liter. So you remember that mu, it's a center of this distribution, right? This is fixed because it's our null hypothesis is 20. But now this one is 22, and this one is 25. So it gets more further away from the null hypothesis. And look, of course, it will reduce the distribution of the areas, right? So the green area is getting bigger and the red area is getting smaller. So now the power is almost 97%. So it means that you have 0.97% chance before you start your experiment, you have 0.97% chance to see this contamination level if this is your null hypothesis, this is your significance level, and this is your sample size. Okay. So the more larger effectors, and in this case effect, it's a difference between null hypothesis, which is no effect, you remember, and the alternative hypothesis, which is the reality in this case, the more larger effectors, the more chances that you will be able to see it. Okay. Now, the second thing, it's a sample size. Sample size is also very important. So again, I come back to the initial case where I have the 60% chance to make type 2 error, 40% it's our power, and the sample size is 10, you remember. What happens if I increase sample size to 30? So instead of 10 glasses of water, I will analyze 30 glasses of water. So in this case, you see that I didn't change the position of the peaks, but what I changed the variability, because you remember that variability of average values of your samples depends on the sample size. And in this case, the variability is smaller, and it leads to better separation of these two curves, the curves that we test for, that we use for making the test, and then the reality curve. And that gives us a power of almost 85%. So by increasing sample size, you can really increase the power. Moreover, that should be your main tool to increase the power. So the larger sample size is, the more power you have, the more chance you have to observe an effect if it's present indeed in your experiment. Okay. And lastly, the significance level. You remember significance level can also be important for type 2 error. So first of all, significance level, it's a chance for type 1 error, but it also can influence type 2 error. How? Well, again, I came back to the initial situation where I have, this is my null hypothesis, significance level, sample size, and remember, the power in this case is 40%, right? So 0.40. What happens if I use smaller significance level? So I say, I would like to decrease chance for type 1 error. So I would like to use alpha of 0.01. And then you can see that it makes a negative impact on my power because significance level is smaller. What it means? It means that this line will be moved towards the direction of the extremeness, right? So you can see that now the line is here, the position of the line is here, and of course it influences the distribution of these two areas. So in this case, the power is almost 4 times smaller. And that's one of the reasons why people don't like to use small alpha, because if you want to compensate the effect of small alpha, you need to increase the sample size. And that's something that leads to additional time, additional resources, and so on and so forth. And that's why in many cases people stick to this default value 0.05, because in this case they at least do not impact power negatively. But once again, this is a bad situation because alpha should be defined only based on the risks of making type 1 error. You shouldn't think about type 2 error when you defined alpha. And then after you made a correct, educated decision about alpha, after that you try to avoid type 2 error by, for example, regulating the sample size. That will be the correct choice. So this is the final overview. So we have two types of errors. Type 1 error, chance to make it, it's alpha, it's your significance level. Type 2 error, chance to make it, it's beta. And beta depends on many things, while alpha, it's something that you defined. And since you never know if the null hypothesis is correct or not, the only way to make your experiment and make your test correctly is to try to reduce chances for both. And now you know to do it, how to do it, right? So you need to reduce alpha, and then you need to increase sample size, and how to calculate the correct sample size we will discuss in a minute. What is very important, I will repeat it again. You should do all the things before you collecting a sample and then never change it. So you should fix it. Otherwise, it's really very tempting to change it to get better results. Don't do that, because otherwise your statistics will not work. Okay, you remember everything is random. So you need to define all rules, all thresholds before you start your experiment. Now let's take an example. So I test the contamination level of water in the lake, the same situation I said before. This is my null hypothesis. So in this case, you can see I have a little bit larger accepted contamination level, 30 milligrams per liter. I want to work with alpha 0.01. That's the chance to make type 1 error. And I would like to see this contamination level with this chance. Okay. So I say if contamination level is 35 or larger, I should have 99% chance to detect it using this procedure. The question is how big your sample size should be. So how many glasses of water I should take in order to have this power at these circumstances. Well, this is what is given, right? So first of all, test. It's a one sample t-test and it's a right tail test. That's what we discussed recently. Now, size of effect. It's a difference between my null hypothesis average and the reality I want to detect, right? So in this case, the size of effect is 5 milligrams per liter. Significance level is given, 0.01. Power of test is also given, 0.99. What is not known is the sample size. However, in order to make a power, we also need to know standard deviation. Of course, we cannot use standard deviation of population, it's not known, but what should we do? We should estimate standard deviation of the sample. So it means that we need to make some preliminary trials. For example, take, 5 glasses of water before you actually start the real experiment and compute standard deviation of these 5 glasses of water, of the nitrogen in these 5 glasses of water, total ammonia nitrogen. And that's what I did. So this is my standard deviation based on the preliminary trials. Okay. Now I can compute the sample size for the main trial, for the main experiment. In this case, I use a function power t-test. It's an R function that computes power or any related things like sample size, like size of effect, like, for example, significance level and so on, based on the t-distribution. Okay. This is what I provided. Look, delta is the size of effect. SD, it's the standard deviation I estimated. Significance level is alpha. Then type of test, it's one sample test. In the next learning sequence, we will also learn 2 sample t-test. And then alternative, in this case, you shouldn't specify which, is it greater or less, you just say that it's one-sided. That's enough because we are working with positive delta always. Okay. So look, I specified all the things, also power, but I didn't specify the sample size. And that's an indicator. So the function will return sample size to me. So this is outcome of this function. You can see all the things I provided, but this one is computed. So you can see the sample size is 15.4, which I can round to 16. So that's how many glasses of water, how many physical samples of water I should analyze in order to get this power for seeing this effect, assuming that this is the null hypothesis and this is the significance level. 16 glasses of water. Now example 2. I have the same situation, same null hypothesis, same alpha, and now the number of glasses of water, number of physical samples is fixed. And in this case, I would like to compute a power. So if I can't use 16 glasses of water, Can I do it with 10 glasses? Of course you can. But how likely I will be able to see that indeed the lake is contaminated if the total ammonia nitrogen is 35 milligrams per liter or more? Well, the same situation. Now I have all these cases, but I have also sample size, but I don't know the power of test. Again, I need to use the standard deviation that I estimated before, right, by using some preliminary trials. And I run the same function. I provide everything, all the same parameters. However, in this case, I provided a new parameter. It's n, but I didn't provide power. So now the function knows n is known, power is not known. It will give me a power. So you can see the power is approximately 0.88. So in 88% cases, I will be able to see this contamination level. So it means reject null hypothesis, of course, right? If I use 10 glasses of water instead of 16. Remember, with 16 glasses of water, the power is 99%, while with 10 glasses of water, it's 88. Okay. And then the last example, again, the same situation, but now both power and the sample size is given. So what I can compute? I can compute the delta. I can compute the effect. How big the effect should be, so I can see it with this power using this sample size, using 10 physical samples. Okay. Same situation. I defined all the parameters, but now the size of effect is not known. Standard deviation. I use the same function. I provide all parameters which are known. In this case, both power and sample size are known, but I didn't provide delta because delta is something that I'm looking for. And that's the delta. You can see 6.7 approximately. So that's the difference. So it means that, you see, I tested for 30. It means if I have 36.7 or larger, I will be able to reject null hypothesis, this null hypothesis, if this is the real contamination level with 99% chance. Okay. So that's how it works. So now you also know how to calculate the correct sample size. As I said, it also depends on the test. So you should define which test to use, for example, t-test, or we will learn some other tests also in this learning sequence. And then you can compute the correct sample size for given null hypothesis and for given alpha and for given power and size of effect. I also have a Grasta app, which helps you to understand the power of test and type 2 error even better. So the next video will be about this Grasta app. It's a short video telling you how to use this app. And then I recommend you to go to Grasta, play with this app, and then come back for the next step where we'll be talking about the sample quality.